Is it okay? Yeah. Okay, so let's start. So far, just to remind you, what I have been doing is actually to develop some basic techniques of random matrix theory. And so today what I want to do is to, show you one sort of concrete application, which is more recent stuff. And I already alluded to it in my first lecture about cold atoms. And so the purpose of this particular lecture is twofold. So number one is to, I already mentioned you that, last lecture we did the semicircular law for the density of states, average density of states, using the Coulomb gas approach. And I said that, it was, Coulomb gas approach is very good for global observables, okay, so average quantities and so on. But if you want to look at the local fluctuations, for example, if you want to look at the spacing distribution or the correlations between eigenvalues very close to each other in the bulk or near the edge, then the Coulomb gas approach is not particularly appropriate for it, and you need to develop some local approach. And so what I want to do is to develop sort of local correlations in the bulk and the edge. For GUE, I want to do it through this example of cold atoms because you can develop techniques, but sometimes they are very dry, so it's always useful to take a nice example and understand the techniques through that example. So this is the sort of one purpose of it. And the second thing is that, as we'll see that as I go on, this will sort of nicely tie up with what Herbert has been talking about. So there will be a very nice link to this KPZ equation that he already talked about. And in fact, in today's lecture, there will be, the same phrases that Herbert used, namely kernel, determinantal process, Fredholm determinant, all these things will come up again. It will be a little bit of repetition, but a little bit of repetition is actually not so bad because, once, somebody famous, I forgot whom, who sort of said that, what do you mean by understanding? Okay, this is understanding is just familiarity. You just see it first time, you don't understand anything. Second time, you understand a little bit better. By the time you have seen 10 times, you have become the world expert on it, okay? So, Wonderman? Okay, maybe, thanks. Okay, so this is the thing. So we'll see some repetition of the same objects that you have already seen. And here it will be, Herbert was developing it for the PNG height model. And here it will be sort of very simple non-interacting fermion models. Okay, but essentially the idea is the same, the determinantal process. Okay, so this is a subject that we have been working for last 4 or 5 years. So okay, I'll just use these slides, but mostly I'll do it on the blackboard. But just to first, I want to sort of acknowledge my various students, postdocs, and collaborators. So there are 3 students. Ricardo Marino has already finished his PhD on this subject, and Aurelia Grabs and Bertrand Lacroix, they are doing their PhD right now at LPTMS, and the postdoc is Jacek Grela. And I've had this sort of nice experience of collaborating with several people, and including Pasquale, who is not yet here, and David Dean from Bordeaux, and Pierre Ledusal from LPTNS. And at LPTMS, there are 3 of my collaborators, Alberto Rosso, Gregory Scher, and Christophe Texier, and also with Pierre Vivo from King's College in the early part of this work. And there have been several references. I don't want you to write down all the references, but maybe I can just upload this slide here in the school webpage so that if you need anything, you can look up at it later. But the point is that you have been very active in this area because this is a very, very simple system, as we'll see, and it's sort of simple yet non-trivial physics you can derive just using basic techniques of RMT. Okay, so that's the sort of idea. So here is the sort of plan. What I'm going to talk about is I'll talk about a very, very simple system, n spinless non-interacting fermions in a harmonic trap in 1D first at 0 temperature. And we'll see that there's a one-to-one correspondence to these GUE random matrices that I've been talking about. And so we'll establish that first. And so at 0 temperature, therefore, in these cold atom systems, so you'll set this sort of new interesting age physics, which is the the fluctuations of the rightmost fermion position, and this will be the Tracy-Widom distribution of GUE. And this sort of gives a very nice physical system where GUE applies, and then maybe later half of today or maybe tomorrow, I'll talk about the generalization to finite temperature. And here you will see that there is this unexpected connection to KPZ equation. Finite temperature in this cold atom system corresponds to finite time in the KPZ equation that Herbert talked about. And then we'll talk about the generalization to higher dimensions of this free fermionic system. And then I'll just summarize and conclude. Okay. So this is the sort of plan for today and tomorrow, if depending on how it goes. Okay. So just to remind you, these slides you have seen before. Just to remind you again that as I said that there have been various beautiful experiments in cold atom systems. It's a very easy system to manipulate, and that allows us to study the quantum and statistical behaviors in quantum many-body systems. And interesting quantum many-body effects happen even in the absence of interaction. So for instance, as I said, for bosons, it's Bose-Einstein condensation. And for fermions, just even though they are non-interacting, there will be Pauli exclusion principle, which actually gives rise to this. So this Pauli exclusion principle plus this harmonic trap, confining potential, this actually induces a rich many-body physics, and that's what we are interested in. Okay. So this is the typical setup. So you have this trap. It doesn't have to be harmonic. It can be any confining potential, and you have this, free fermion. I'll talk about fermions from now on. So you have these fermions which are trapped here, and you want to know the quantum fluctuations or the thermal fluctuations of these systems. Okay, and so that's the problem. And in particular, as I said, if you are close to the trap, center, then you don't see the curvature of the trap. So there you can apply the traditional translational invariant system techniques that people have developed for many years now. But because of this confining trap, you have these additional edges where the number of particles are small, so the fluctuations dominate. And there, it's difficult to apply the traditional translation invariant techniques, and therefore you have to do something else. And here, the sort of random matrix theory comes into help, and determinantal process that we'll see. And so our focus will be the edge physics, basically. Okay. So now I'll go to the board. So this is the problem that I'm interested, but I just want to, just so that we are talking in the same language, so I want to sort of repeat some basics. Most of you know this, but just to set up my notations. It's extremely basic stuff, many-body physics. Okay, so this is a standard textbook stuff, but just to set up the notations. Imagine that again, I have a confining potential V of x. I'm talking about one dimension, but you can easily generalize to higher dimensions. And so first think of a single particle. So you have a single particle. So single particle has this Hamiltonian, which will be minus h bar square over 2m. So I'm talking about in continuum, not in lattice, plus this potential V of x. Okay. So this is the single particle Hamiltonian. And so the eigenfunctions and eigenvalues so I'll be talking totally in the first quantized notation. So I'll denote by phi kx as the eigenvalues. So this will be some spectrum, and the spectrum will be discrete spectrum. Okay. So these are the energy eigenvalues in general. and these are normalized to 1 usual, and this is the sort of single particle eigenvalues. Okay, and these phi kx are normalized over the full real line. Okay, and so this is just basic quantum mechanics tells us this is just the probability. Then you can think of this as the probability density due to quantum fluctuation of a single particle. Okay, and so for instance, if I use the harmonic well, then this is just a solution of quantum harmonic oscillator, textbook stuff. So we have the phi kx, which will be some normalization times exponential minus times the harmonic polynomials. So where the alpha is square root of m omega by h bar. So this is the frequency of the trap, and these are harmonic polynomials, which are okay. So for instance, even in the ground state, you have this. So even in ground state, so ground state means k equal to 0, and so there it's just a normal Gaussian. So you have still fluctuations because of the quantum fluctuations. Okay, and these harmonic polynomials are just orthogonal polynomials like this that everybody knows. Okay, so this is a single particle system. So now we look at the many body system. So that means I have n particles. In a confining trap. So the Hamiltonian for the many body system in general would be so this is the kinetic energy, then you have this potential energy due to the trap, and in addition you could have interactions between the particles. Let's say this is a two-body interaction. Then you can have 3-body, etc., etc. Okay. And the general goal of many-body theory is to find the many-body eigenstates, okay, which I'll denote by psi e, which are the spectrum. So these are eigenstates of this object. So this E is the total energy. So in general, of course, it's a very difficult problem. I mean, when you have interactions, okay. So we'll consider a very simple case, which is that there is no interaction. Okay. So it's non-interacting system. So now before that, you have to sort of say something about the statistics of particles. So this is the quantum statistics of particles. So they can be either bosons or fermions. Or more generally anions and things like that, but let me not get into those. So this is the additional, so this provides an additional symmetry of the many-body state, right? So you know that for bosons, it just says that if I exchange any two particles, let's say xi, so then under this exchange of ith and particle jth particle position, it should be exactly same, symmetric. So this is a symmetric, and for fermions, When I exchange, I get a negative sign. So they are antisymmetric with respect to exchange of any two particle position. So as a consequence of the antisymmetry, so what you see is that for fermions, if any two coordinates become equal, so for example, if the ith and jth coordinate becomes equal, this is exactly equal to 0, because if it's a continuous function, so this symmetry under exchange, it has to be 0. And this is what we know as Pauli exclusion principle in real space, which means that two fermions can never be in the same position. So the probability of having two fermions, probability is because this is, in that state, this object is just the probability density, quantum probability density. Okay, so the probability density is exactly vanishes when two fermions are in the same position. Okay. So now let's look at the non-interacting case. So I want to construct this many-body waves, many-body eigenstate. So any many-body state is very easy with non-interacting system, because you can always construct a state, any state, as if we just take the product of the individual states. Okay. So if I take, for example, one particle in state K1, another particle from state K2, etc. In general, for whatever the K1, K2, etc. are, this certainly satisfies the Schrodinger equation with energy, which will be the sum of these single particle energy states. So this state is certainly an eigenstate of the many-body state. Okay? But it has to, in addition, satisfy the statistics, the statistical constraints, Bose-Fermi. So it cannot be just any arbitrary state, because here, for example, I can exchange any two particle positions and it won't satisfy this symmetry, right? So you have to do something else in order to so that it satisfies in addition the symmetry of the statistics. And so just again, this is very basic stuff, but I'm just setting up my notations, if you like. So for example, if I have n equal to two particles, so if it is boson, then you can construct just take a symmetry combination of that, some normalization. So I just symmetrize the two positions. Okay. Then each part is satisfies Schrodinger equation with the same energy E, and therefore their sum also satisfies the same Schrodinger equation with energy which is K1 plus K2, right? And this will be generalized to any n particle system. So you just have to take the symmetry combination. Okay. And for fermions, for two particles, for instance, you have to take the antisymmetry combination. Again, okay, here, you can put a 1 over root 2 if they are normalized. Okay, so if I take the antisymmetry combination, then it satisfies Schrodinger equation with the same energy epsilon K1 plus epsilon K2, because each of the individual term is a solution of this Schrodinger equation with the same energy E. And in addition, it satisfies this fermionic constraint that this has to be 0. Okay. And this guy here, you see immediately that you can write it as a determinant. It's a 2 by 2 determinant. So it's just phi k1 x1, phi k1 x2, phi k2 x1, phi k2 x2. Okay. So in general, if you now go to n particle system, sorry. So again for bosons, we just write a up to a normalization constant here. So here is sum over all permutations, and you just take the product of the different permutations. So just exactly analog of the n equal to 2, but it's a symmetric combination. Okay, sigma is over all permutations, and for fermions, okay, this is also 1 over n factorial. Okay, just some normalization, doesn't matter. Sum over all permutations, but you have to put a sign for the permutation. So each time you permute two coordinates, you have to put a minus sign. So for even permutations, even exchanges, it will be +1, and for odd exchanges, it will be -1. Okay. So this is an allowed many-body fermionic state, and of course, this is just a determinant. Just like the 2 by 2 case. So determinants with elements which are this phi ki xj, ij. So it's an n by n determinant whose elements are just the single particle wave functions. And so whichever state you are occupying, so now clearly you see that, you can see from this example, if k1 equal to k2, if I put two particles in the same state, this is identically 0, okay, which means that in fermions, you cannot, not just in position Pauli exclusion principle, but even in the energy direction, you cannot put two particles in the same state. Okay, so same thing here. So I mean, for n particles also, I cannot put two fermions in the same energy state. So I can pick up, any state just by, but the only constant is I have to put only one fermion in each state. So for example, I can take this guy here and that guy here and maybe another guy here for 3 particles, or I could take the first 3 or whatever. Only constant is that I cannot put 2 particles in the same level. Okay. So this has a name. So this is the famous Slater determinant. Okay. So this is the first point, and so now, given this particular state, which can be any excited state also, so consequences. So if I, in that particular state with energy E, and the energy E of that state is just the sum of the single particles, sum of the occupied levels essentially. So I can, this would be the sort of quantum probability density in that particular state. Okay. So this is just 1 over n factorial determinant square. Well, in general it will be phi I star phi xt, but in our case it will be harmonic oscillator. Let's say it's all real functions. So now determinant square of A, so determinant of AB is determinant of A times determinant of B, right? So therefore, the product of two determinants is a single determinant, and this single determinant, its elements. So if I look at what is the ijth element of this matrix, so this will be aik bkj, sum over all k, right? So think of this as a product of determinant of A, and B is equal to A in this case, okay? And then just apply this thing. So therefore, this will be 1 over n factorial times determinant of sum over all k, k belonging to occupied sites, occupied levels. Okay. I'm just using this, ijth element, you have to sum over all k. So here, you just, because, you think of the matrix and your entries are this k, which characterizes the entries. So you just, this is exactly equivalent to this statement, okay? So therefore, the energy state, the probability density of that particular energy state, you can always write as a single determinant whose elements are, so you take the wave function, whichever are the occupied states, and you just look at the single particle wave function and put one coordinate here, one coordinate there, xi, xj. So that's your ijth element of your matrix, and you just compute this determinant, okay? So this is the structure, and so any many-body state for fermions. So from now on, I'll just talk about, okay, in general, okay, can be labeled by the occupation numbers, right? So this nk is either for fermions, so nk is 1 if the kth level is occupied, and 0 otherwise. Okay? So then, this just says that in that particular state, which is labeled by nk, many-body state labeled by nk, so then the many-body wave function square, I can write down as 1 over n factorial times determinant of sum over nk for fermions. Where k is now summing over all possible states. So this will obviously pick up only those which are occupied, and then you are back to that. Okay. So this is for any excited state. I can always write it as a single determinant, many-body state, and which is characterized by these occupation numbers. And the energy of this state is clearly then summation nk epsilon k. Okay. So this is the sort of very basic thing. And here ij, so this is a determinant of n by n matrix. So let me call this object, let me use my notation, so Kn. Yeah. Yes. Yeah, because I mean, okay, just do it by yourself. This is a homework, okay? Do it for n equal to 2, n equal to 3. You can convince yourself, okay? This is very simple, okay? All right, so So therefore, any state, okay, so far I've not talked about ground state. I mean, I'm just talking about any particular fermionic many-body state. You can always write as a determinant of some object, which I'll call kernel, okay? And in a minute it will be clear why this is called kernel, okay? And so this kernel associated to that particular many-body state is characterized. So this kernel in some sense depends, depends on the labeling of that occupation numbers. So you give me the n case that characterizes the state, and then in that state, for every such excited state, there is a kernel which is defined as the sum over all occupied states belonging to that level. Okay. Now, so far I didn't say anything. This is, I'm just giving a name. Okay, that this is a kernel. What does it mean, kernel? Okay. So now, so you have to remember this. This is the sort of basic result here. Okay. So given this, so now let's focus on first on the ground state, and so suppose that your system, the temperature is 0 and you are exactly at ground state. So ground state means what? That you have to just occupy. So because total energy is sum over nk epsilon k, so this will be minimized when you take only the first n levels, right? So you occupy the first n levels. You put one particle here up to this. So this is what is we call the Fermi level. Okay. Okay. So in that case of the ground state, so then the ground state, I write down this as E0 or psi 0, let's say. So ground state many body wave function is therefore 1 over n factorial times determinant of this k xi xj I less than j, where this k x y is simply just phi kx phi ky sum over k from 0 to n minus 1, okay? Because you occupy the first, starting from 0, I'm calling it this as 0, or you can call it 1 if you like, up to n minus 1. So the ground state wave function, I can always write it this way. Okay. Now let's just, okay, so far this is very general, okay, and the ground state energy is just the sum over epsilon k. K is going from 0 to n minus 1. So let's try to evaluate for harmonic oscillators. Okay. So what does this wave function looks like? Sorry, this is square. What does the wave function mod square looks like? Okay. So remember that I have these single particle states which are given by the Gaussian times Hermite polynomials. Okay. So I want to construct the Slater determinant, as I said. So this is the ground state wave function, determinant of the ground state wave function. Okay. And so now it's a simple, again I keep it an exercise. So think of two particles first, okay? So you have the, let's say alpha 1 square x1 square over 2 times Hermite polynomials of degree 1, sorry, alpha x1. So this is a 2 by 2, so I'm just computing the psi 0 x1 x2. So it's a determinant of okay. So you want to calculate this determinant. So obviously, you can take out this common. So these Gaussian factors, they just go out, right? Okay, from each column, I can take out this factor, and from this column, I can take out this factor. So what I'm left with is just the Hermite polynomial, determinant of Hermite polynomial. Okay, so that's this step here. Okay, so all I'm left with is just the determinant of Hermite polynomial. Okay, but the determinant of Hermite polynomial is actually very, very easy to compute, right? Because Hermite polynomials are, remember, these just orthogonal polynomials like this, right? So you can explicitly evaluate this. So let's just see an example. Okay, so take n equal to 3. So I have this object, right? So I write down this object. So 1, 1, 1. 2x1, 2x2, 2x3, 4x1 square minus 2, 4x2 square minus 2, 4x3 square minus 2. Okay, but you immediately see that you can take out these 2 from the second row outside the determinant, and also you can multiply the first row by 2 and add to the third row, so that these 2 will cancel with that. So if you just do this simple exercise, you find that you can bring it to this form 1, 1, 1, x1, x2, x3, x1 square, x2 square, x3 square. But this is a van der Monde determinant, okay? And this determinant you can easily evaluate, and this will be up to a numerical factor. This will be just x1 minus x2, x2 minus x3, x3 minus x1, okay? And so now it's a homework. You do it for n by n, and you will find that this will be just the product of xj minus xk j over k. Okay, so if I do this n by n Hermite polynomials, and this is true for any orthogonal polynomial, in this case it's Hermite, and so what you see is that the ground state of the harmonic oscillator, so you have the ground state wave function, which is just product of Gaussians times this van der Monde determinant. Okay, so therefore the square of that, okay, it's up to a normalization constant. This normalization is such that the total probability is 1. You only integrate over all x1s, because this is the wave function's mod square. So this is just this. Okay, so up to this factor alpha, you see this is exactly the joint distribution of GUE, right, that I talked about in the first few lectures. So just to remind you again, GUE, remember that we had this matrix and we took the entries as Gaussian random variables and complex Hermitian case, and so there is trace J dagger J, so it's invariant under a Gaussian unitary rotation. And then we proved, I mean, I didn't prove it for the GUE, but did it for GOE, but it's the same thing. You can calculate the joint distribution of eigenvalues, which is just this Gaussian times lambda J minus lambda K square. Okay, so immediately then you see that there is a exactly one-to-one correspondence between these two problems. Okay, so in the quantum case, fermionic case, squared many-body wave function in the ground state for the, so this is just exponential minus summation alpha square xi square times the van der Monde square, where alpha is this just a constant which is the inverse length, which is square root of m omega by h bar. Whereas for the GUE eigenvalues, sorry, yes, okay, thanks. Okay, for the GUE eigenvalues, you have exactly same as here. So there is a one-to-one correspondence up to this factor alpha. The positions of the fermions in a harmonic trap at zero temperature, their quantum fluctuations are exactly described by the joint distribution of the GUE eigenvalues. Okay, so this is the sort of very nice physical application of GUE, okay, that you see, and and indeed, I mean, using this mapping to random matrix theory, and random matrix theory has been well developed, so many things are known, so you can actually extract a lot of results for these very simple fermions in a quantum harmonic well, just by just dragging the results from RMT literature, and this has been used quite a bit in the recently, I mean, as we'll see, so several, spatial properties of free fermions in a harmonic trap at zero temperature, you can directly obtain from RMT. For example, number fluctuations and the spacing distribution and things like that. You just make a, dictionary from one to the other, and you get the results. And you can even apply things, which doesn't have any random matrix analog. For example, you can ask what is the entanglement entropy of a particular interval in the ground state of fermions with the rest of the system. And so this one, again, you can use the techniques from RMT, which I'm not going into the details. You can look at this paper with Pasquale and Pierre Ledusal and myself. So we could say a lot of things just using the RMT techniques. Okay, so just to tell you. So the conclusion is that okay. So conclusion is that this is GUE sort of, this is a very simple physical relation of GUE, okay, the ground state wave function square. And so now what I'll just use this language to develop this correlation structure that I mentioned, okay. So without, just with this example, just keep this example of fermions in your mind so that you see exactly, you could develop this correlation function technique without using this fermionic language, but I find it easier somehow to use the fermionic language so you can see exactly what is going on, okay. All right, so I've told you that I've defined this object which I called kernel. Why do I call it kernel? I mean, so the reason is, okay, so here is a sort of definition. Again, I mean, I'll just repeat what Herbert has said already. Okay, so now we want to, so we have the joint distribution, we want to calculate the correlation function, okay? So generally, I mean, m-point correlation function. I had already defined that in one of my previous lectures, but the way I would define it is Rm of x1, x2, x3, xn. So this will be, you remember that there was a combinatorial factor I just needed. And then you just take your joint distribution, which in this case, just this object mod square. So you keep the first m coordinates fixed, and you integrate over all the rest. So this is the definition, okay? So special cases, if I choose m equal to n itself, okay, then this is just the joint distribution, right? Because if I put m equal to n, so you have just, joint distribution up to factor n factorial times okay, so that means it takes all the endpoints, it keeps all the endpoints, it doesn't integrate over anything, it's just this, but this is up, and you see why I kept the n factorial. So you see that this is just exactly determinant of this kernel. So kernel is, again, remember that this is just single particle wave function sum over k equal to 0 to n minus 1, okay. So this is the sort of overall joint distribution, okay, so which is the determinant. And then if you choose, for example, m equal to 1, that means I just keep only one coordinates. So then this will be n minus 1 factorial, so that will cancel, so you get a factor n, and then you have this. So you keep the first coordinate fixed x1 and integrate over all the other coordinates. And if you remember that, this was exactly the, so this is a 1 point marginal, and this was exactly the n times the average density of states. Okay. where this is defined as 1 over n delta of, okay, let's call it x. Because remember I said in the, I don't remember which lecture was it, but that the 1 point marginal is exactly same for any arbitrary joint isotropic arbitrary joint distribution, is just this average density of states. Okay, and similarly, if you calculate m equal to 2, this will give you a 2-point correlation function. Okay, so R2 of x1 x2 is just n into n minus 1 times this object x1 x2 you fix and integrate over all the other guys. Okay, so this is the definition of all these correlation functions. Okay, so now I have this object here, okay, which is the overall joint distribution m equal to n, and can I calculate the the lower order correlation functions from this? Okay, and so here comes the, yes, 1 point marginal, yes, which is exactly average density of states. Yes. Largest eigenvalue? How it will scale with n? I'll come to that. I have not come to largest eigenvalue yet, right? So it's just a 1 point, but this is exactly what will give you Wigner's semicircular law. Okay. So largest eigenvalue will scale like square root of n. Okay. So, all right, so you define these correlation functions, and now the question is, how can I calculate this correlation function? Can I mean, if you give me this, can I calculate the correlation functions? Okay, and here comes the definition of a determinantal process. Again, I'll repeat what Herbert has already said. So determinantal process is the process such that, this is definition, okay, that any m-point correlation function. So you saw this, n capital, when m equal to capital N, you can write it as determinant of this kernel. Okay. Now, if it so happens that any m point, m can be anything from 1 to n, if I can write this also as the determinant of the same object, same kernel, but now it's an m by m determinant. Okay. If this is true for all m, then such a process, so you take any point process, and if it satisfies this property, that means any m-point correlation function I can write as a determinant of the same object. Okay, it's just the size of the matrix changes depending on your order of correlation. Okay, then such a process will be called determinantal. That's the definition. Now, what is the advantage of this? Of course, the advantage is you can, just by computing one quantity, you can calculate all the correlation functions. But the main question is, how do I know? How the hell do I know whether a process is determinantal? Okay, I'm not going to calculate all the m correlation function and check that this is valid for all m. Okay, then it's as good as doing the calculating the correlation function. Okay, so you have to have some, some other ingredient to tell you whether a process is determinantal. Okay. And here it's actually very useful. So I'll not, so question is, when is a process determinantal? I have not said, this is the process. I gave you the xi xj, right? I gave you the wave function square. So this is definitely, I have not said, I'm saying that any process, okay? Process means it's just joint distribution. That's it. Okay. It's generally called process because often you can have also time dependence in it. Okay. No, here you don't have it. So but in general it's called process. Okay. So when is it determinantal? So the statement is that if you can write down the full, so this is true for any joint distribution. So suppose I have a set of variables, some joint distribution like that, and suppose that you are able to calculate this as this is basically given by up to some constant here as a determinant of some object k. So then there's a theorem due to, originally it was due to Mehta for when there is no time dependence, and more generalized theorem is by Ena and Mehta. Which says the following, that suppose that you first get your joint distribution, and suppose that you could write it as a determinant of some object. Then this object, if it satisfies what is called the reproducibility property, so let me just write it down carefully. So if it so happens that this k function of reproducibility property, that if it is like this, and you integrate over all k, all y, and if it is same as kn of xz. So the procedure is clear, right? You give me a joint distribution, and maybe I'm able to write it as a determinant of some object, and then I just have to verify that this object satisfies this property. If it does, then you are guaranteed that any m-point correlation function you can write as a determinant of the same kernel that was there in the original joint distribution n-point function, right? So procedure is clear, right? So I have this, you gave me the n-point function, capital n-point function, and I first identify this object, if it can be written as a determinant, because many places you cannot write it as a determinant. If you can write it, and after that I just verify that it satisfies this property, and if it does, then the process is determinantal. So there's a sufficient condition. So this is the sort of this thing. So let's check in our case whether it satisfies or not. So let's check. So we know that this we have been able to write as a determinant, and now let's check this. So just substitute this. Yeah. No. This has to be exactly 1 here. This has to be exactly 1 here. I have not proved this theorem, but it will take me a long time to prove. But you have to take it my words for it. I just wanted to show you that it works for our case. So in general you have phi k star x, but since you are doing harmonic oscillator, it's a real function. But in general it will be the complex conjugate of that. So xy. And then you have phi k prime of y star times phi k prime of z. So let's forget this complex conjugate for the moment. Yes. And then I have to integrate over y. So now the point is that when you integrate over y, you see this phi ky are single particle orthonormal eigenfunctions. So therefore this integral here over y, that just gives you a delta function. So then you are back to this phi kx, phi kz, which is precisely kn of xz. Okay. So in our case, that is for the GUE, or if you like, particles in harmonic potential, fermions in harmonic potential, it does. So you can identify a kernel, and the kernel satisfies the reproducibility property, and therefore we are guaranteed that this is a determinantal process. In the sense, any m-point correlation function where m is between 1 and n, I can always write in terms of this kernel, okay, determinant of this kernel, which is a smaller m by m determinant. Sorry, okay. So I should stop here, and then we can continue after this. Okay, good. Thanks. Okay, so okay, after this sort of basic, so what we know now, it's a determinantal process. At least we have verified. So okay, this is just a repetition of what I did here. So psi naught square is just a product of the two determinants. You can write it as the determinant of a single object, and this single object is the kernel. Okay, and it verifies this property. And so as I said, any m-point correlation function, then you can, these are the two extreme cases, m equal to m and m equal to 1 and m equal to n. But for any n, okay, and just one thing, there's again, I mean, I said it already, but m equal to 1, remember, is related to the density. Okay, so what you see is that the average density, therefore, in the ground state is as a very simple structure, namely so average density is just 1 over n times R1 of x. Okay, but we said that the Rm, so if I put m equal to 1, is just a 1 by 1 determinant, right? So therefore this is just 1 over n times the kernel itself at identical points. So 1 by 1 determinant, right? Xx. So therefore you have an exact formula for any n for the average density of states, which is so this is exact. Where this phi kx, remember, is just a Gaussian times Hermite polynomials. Okay, so therefore, if you plot this, so as you increase your value, just plot this, just plug it in and plot it in the Mathematica, what we'll see is that as n increases, so this curve looks like this. Okay, I'm not drawing very well. Functional. So as n increases, the whole thing changes. But what you see is that typically there are oscillations. We'll see a picture soon. There are oscillations here, and then oscillations near the edge. And eventually, in the large n limit, this should approach in the scaled form. Once appropriately scaled, this goes to the Wigner semicircular form. So remember, we derived Wigner semicircular form in the large n limit directly by the Coulomb gas approach. But here, this is an exact formula for any n, and you can plot it and see how it approaches. And in fact, just by using the properties of the Hermite polynomial and Gaussian, you can get the asymptotics, and you can actually write this. You can show, I mean, I'm not going to show this, but you can show that this, let me get my note correctly. Yeah, so in the large n limit, So if I now take the n going to infinite limit, and I just use the asymptotic properties of harmonic polynomials and so on, so this actually goes into this scaling form. Where this function f of z is precisely this 1 over pi square root of 2 minus z square. Okay. So this is sort of alternative way of deriving the Wigner's semicircular law, if you like. Okay. And so yeah. I'm coming to that. 1 minute. So good question. So this is sort of, as I said, this is a beautiful determinantal structure for this problem, and you can see that this is also, I mean, those of you who are familiar with Wick's theorem in fermionic physics, this kernel, this is nothing but just the fermionic creation and annihilation operator at 2 different points. Okay, so this is the central object, and in particular, this average density is precisely has this form. Okay. So basically, this theorem, you can call it Enameda theorem in the general case, I mean, in the determinantal case, but, this is basically a consequence of Wick's theorem for fermions. Okay. So average density of fermions. So this is exactly what Marcus was talking about. You see, this is just, you can get this thing very easily. In fact, this is what the cold atom people did. This is just a local density, what they call the local density approximation or Thomas Fermi approximation. It's a semi-classical approximation. Which just says that, that okay, if you look at a particle, the free fermion, so p square over 2m kinetic energy plus potential energy is the total energy E. I mean, for each particle. So, think of semi-classically. So, in the phase space xp plane, so each point, denotes some energy states, and you fill up to the Fermi level, all these individual energy levels, energy states, and so therefore, you see this momentum p goes from square root of 2m epsilon minus vx plus minus. So at a particular point in x, so this is, you are going from minus p square root of epsilon minus vx to plus square root of epsilon minus vx. Okay, so this is these things. So if you ask what is the density of states at x, so you just have to just integrate in the direction of p, and that gives you a density of states in this semi-classical approximation, which is basically proportional to square root of this epsilon is just the the Fermi energy basically. Okay, so which in our case will be n h bar omega for harmonic oscillators. So this is the Fermi energy. Okay, and you see for harmonic oscillator, this is just Fermi energy is just, remember, this is the sum of the single particle levels, and therefore the Fermi energy is just n, because n h bar omega. So minus half m omega square x square. Okay, and this is exactly this semicircular law. Okay, so this is a very easy way to get semicircular law using the local density approximation, which is of course a semi-classical approximation. It's not a real exact calculation, but it works very well for arbitrary potential. In fact, for arbitrary potential, indeed you will find this. In fact, strangely, in the cold atom community, if you look at, people have been using this semi-classical approximation for a long time. Okay, but without really realizing that this is exactly Wigner's semicircular law of the random matrix theory. So which is, very strange. I mean, well, strange. I mean, if you don't know the mapping, then you don't know, of course. Okay, so this is the thing. So, and this I have already said, so therefore the density, average density of states is this, but now we want to look at the fluctuations from, one sample to another sample, and there are these two, so what you see is that there are these two edges, square root of 2n over alpha. Remember, alpha is square root of m omega by h bar. There are the two edges, and so I'll call this as r edge. Okay, and there's a single length scale which is square root of m omega by h bar. And so the bulk interparticle distance, I have already said that by setting this to be order 1 over n, you gather that, okay, in this notation, I didn't scale it to order 1, so therefore this is square root of n. But you can do the same analysis and you get n to the power minus half. Whereas at the edge, near here, the typical interparticle distance is of order n to the power minus 1/6. Okay, and so therefore, bulk interparticle distance is much bigger than the sorry, it should be edge. It should be much smaller compared to the interparticle distance at the edge, because here the density goes smaller, so the particles are sparser, so they are far apart from each other. Okay, so as a result, there is a lot more fluctuations near the edge as opposed to the bulk, and this is where the RMT sort of comes into the play. Okay. All right. So what are the sort of results from RMT that we can see? So suppose I look at this average density of states now, but I'm looking at not exactly n going to infinity limit where I'll get the Wigner's semicircular law, but I'm looking at a finite but large n, and I'm zooming out just this part at the edge, okay, over a scale of n to the power minus 1/6, and I want to see the local structure here. Okay, I already told you there are some oscillations, and in fact, if you plot it, so what we'll see is that there are these oscillations. Indeed, the density. So all I'm doing is just doing this computation here. Okay, so I'm just taking this guy. I'm just substituting the Hermite polynomial times Gaussian here, and just analyzing this in the large n limit. And if you do that, you can show that this is very simple exercise. I mean, this will be some single scaling function of the some point x. I'm looking at some point x near the edge, minus the location of the edge, which is square root of 2n over alpha, over a scale of n to the power minus 1/6. We have already seen that this is the natural scale, typical interparticle distance. Okay. So once you center and scale it, this is a single scaling function of the scaled variable, and this scaling function is given by Airy prime square minus z times Airy square. Where does this Airy function come from? Again, you see, basically this is, I'm looking at the edge. So this is Herbert already mentioned to you. So if you take your potential Vx and you are looking at distances where x is of order r edge, which is square root of 2n over alpha, plus order n to the power minus 1/6. So you make a change of variable here, right? And you just expand this guy around that. So you just do a Taylor series expansion. So the first term will be a constant, and then the first non-trivial term will be of linear order in n, y, right? So in linear in y, and then you have to find out the wave functions. In order to analyze this near the edge, you have to find out the wave functions of a single particle in a linear potential. You're just linearizing your harmonic, and this will be true for general potential. You are doing the linearizing your potential around the Fermi surface, and so therefore this linear thing, that's what gives you the Airy function, and this is what this guy just comes from that essentially. Okay, so Airy function square minus z. Okay, and so this scaling function actually decays like minus z to the power 3/2. And here it goes like square root of z over 2 pi, because when you go very far away, when z is very large negative number, that means, remember, z is on a scale of interparticle distance measured from the edge. So when it's much bigger than the interparticle distance, that means you are probing the bulk. Okay, so therefore it goes like square root of z, which precisely matches with the semicircular form out there. Okay, because this is the semicircular form. So there is an asymptotic matching coming from the edge regime and the bulk regime. Okay? So that's what happens here. Okay, so now let's look at the kernel itself, because as I said, kernel is a central object. So for determinantal process, I just have to look at the kernel, and then I know in principle all the correlation functions. Okay, so how does the kernel look like? Now in general, this kernel, remember this is the formula for the kernel. And so I have my fermions, whatever positions of these points here, overall semicircular law. So I can take these 2 points anywhere. Then of course, I have to look at this sum, and we can't really deduce any general property of that. So you are looking for universality, which does not depend on the particular choice of this quantum potential, as long as it's confining potential. So where can we expect to get universality? So one thing is that if you take these 2 points x and y near the bulk, okay, very close to the trap center, let's say. Okay. So if I do that, And then I have to analyze this, but then you see that then you'll get a scaling function like this, where this is a sine z by z. This is called the sine kernel. Where does the sine kernel come from? So it's actually simple again. So let's just look at it. Where does it come from? So you see, near the bulk, if I'm near the center here, okay, I don't see the curvature of the potential, right? So I have to solve again the local wave function, which is just d2 phi k dx square. So potential is basically 0 there, right? So this is just equal to epsilon k phi k. So if I set epsilon k to be k square, so these are just plane waves, right? Roughly speaking, locally. So these are plane waves, and where my k is actually going from plus kf and minus kf, kf being the Fermi momentum. Okay, so kf square over whatever, kf square is just 2 pi over h bar square times n h bar omega. Okay, so basically kf square is proportional to n. So these are my single particle, local wave functions there. So if you just substitute it here and replace this sum by an integral, so you will get e to the power I k x minus y. Okay, you have to be careful here. You have to put a star here because this is a complex conjugate, and dk going from minus kf to plus kf. So if you compute that, this will give you the sine function. In fact, sine of alpha root 2n x minus y. This alpha root 2n, remember, is 1 over alpha root 2n is the typical distance. That's the scale, typical interparticle distance near the bulk, okay, divided by pi times x minus y. Okay. So once you have this kernel, you just probe it. I mean, you take these 2 points x and y very close to the bulk and just replace it by plane wave, and you get the sine kernel immediately. Okay. So this is called the sine kernel, and you can see that why is it universal, because it really doesn't depend on the precise shape of the potential Vx, right? And now, another place where you can probe this, when you take these 2 points x and y very close to the edge, okay, both points very close to the edge. Okay. So then, all you have to do, again, do the same calculation, except that you have to replace this phi kx instead of plane wave. Near the edge, you have to replace it by Airy function. Okay. And then this sum again will be replaced by an integral, and you will get what is called the Airy kernel. That means this kernel there, x and x prime both close to the edge. So I can write in this scaling form. This is just the scale distance from the edge. And this scaling function just becomes the area of z plus u, area of z prime plus u. And this is this famous Airy kernel. Okay? And again, you can see why is it universal, because you can always linearize your potential near the edge, and then you get the Airy kernel. So this is the sort of basics of GUE and determinantal process, that I know the bulk kernel, I know the edge kernel, and so now question is that if I calculate some observable, so in general, as I said, any m-point correlation function you can write in terms of this kernel. This is the central object, okay? And similarly, you can ask for other observables, not just correlation functions, and you can write in terms of this kernel, okay? And Herbert already told you this, and so therefore, once you know the kernel, you know essentially everything. Okay, so let's look at this position of the rightmost fermion at 0 temperature, which is exactly the largest eigenvalue of the GUE matrix because of this 1-to-1 mapping. So the point is that the fluctuations of this x max, quantum fluctuations at 0 temperature, are therefore governed by the largest eigenvalue fluctuations in GUE, which is known to be Tracy-Widom distribution that Herbert already mentioned. So what that means is that, again, if I look at the probability, let's say the cumulative distribution of the x max, probability that this is less than equal to m will be a single scaling function of, again, the distance, scale distance from the edge. Our edge is, remember, square root of 2n over alpha. And this is the interparticle distance, typical interparticle distance at the edge. So this will be a single scaling function of something, of this argument. And this scaling function, again, you can write in terms of this kernel, And this is the case of, Tracy, I mean, this is the Fredholm determinant. Now, okay, I'm going to, Harvard has already done it, so I'm not just going to rederive the whole thing, but I just wanted to, mention, remind you again what is the Fredholm determinant. Because, when I first started working on it, I myself was not very sure what is Fredholm determinant. So it's just, good to remember what is it. It's very simple, but okay, just before we do the Fredholm determinant, I mean, it's always good to go back to basics. Okay, so if we have a any matrix, let's say Kij, okay, n by n matrix. So if I want to find out the eigenvectors and eigenvalues of this matrix, so what I'll do is I look at this. This is just a matrix multiplication. This is a vector, and this is a matrix, sum over j equal to 1 to n. So that will be equal to lambda times psi lambda of I. Okay, let's call it x. Okay. Okay, so j. Okay, so this is just a vector. This is a vector of column vector of length n. The entry is n, and you have a matrix here. You're multiplying this lambda equal to same vector, right? So this is, all of us know this, basic. And so now if I want to calculate the following determinant, which is like a characteristic function. Let's say determinant of I, identity matrix minus k. Okay. So this means that this will be the determinant. Okay. K are the K are the lambda is the eigenvalues of this matrix K. Okay, this is the standard these things. So what Fredholm means? So imagine that now I have a line, continuous line. I take any interval, let's say a to b. Just think of this, interval consisting of, just imagine discretizing them very finely. Okay. So I take n points and I take n going to infinity limit. Okay. So this is just discrete points, and I do the same thing here. So then, basically what happens here. So okay, first, okay, you have this interval, and let me define first analog of the matrix, which is an operator here, but this operator has, two indices like the matrix. Matrix has two indices ij. Here you have a x and x prime. Okay, so this is just an operator, x and x prime. So you can think of this as a function of two variables, x and x prime. Forget about it. Just think of function of two variables, x and x prime. And so where x and x prime both belong to this interval AB. Okay. So sometimes you write with a projection P operator here just to indicate that x belongs to this interval AB and x prime also belongs to interval. This is what Harvard was calling chi indicator function. Okay, sometimes it's called projector. Okay, but just says that it's a function of two variables. And so think of this as a sort of infinite dimensional matrix, exactly like this, because you have a infinite number of points over this interval. And the analog of that equation would be, if I want to know the eigenvalues of this operator, so I'll just write this integral equation. This is the exact analog of that, except that this is infinite dimensional integral in these things, and the integral is from a to b. Okay, so this is an integral equation. So you give me this function, whatever function you want to give me, and I just look at the eigenvector of this. So now my column vector is actually has continuous arguments, so it's an infinite dimensional vector basically. Okay, so I have to solve this integral equation and find out the eigenvalues. Okay, and then Fredholm determinant is just exactly, I write with the capital D here, is precisely this object, which is the product over all the eigenvalues. Okay, I here can be anything, so product of all the eigenvalues of this integral equation. Okay, and sometimes, I mean, this of course you can always write down as exponential of log of 1 minus lambda I sum over I. Okay, and you can expand this lambda i's, and you can write down as in terms of the trace basically, right? So it's trace of log. Sorry, log of trace. Yeah. Anyway, so if you just expand this, in lambda i's, imagine that you could expand this log formally, and then you will have, you'll have this series sum minus lambda I square over 2, lambda is cube over 3, etc. Okay. So basically, I mean, to evaluate a Fredholm determinant, you have to somehow find the eigenvalues, for instance, and just evaluate this trace here, or this product of the product of the eigenvalues, and that's what is called the Fredholm determinant. Okay. So here, when I write this, P, so K edge is precisely our edge function. Remember, K edge of any 2 points x and x prime, scaled variables z, z prime, was this integral du area of z plus u times area of z prime plus u, okay, 0 to infinity. So this is a function. So you give me this function z, z prime, okay, and function of these guys, and I have to somehow find the eigenvalues, and I have to just calculate this Fredholm determinant, but I have to specify what the interval is, and the interval here is is given in this this projector, means that is xi to infinity. Okay, so here it says that I have a line and I take some xi to infinity. So this is my interval. So a is this and b is infinity. Okay, so I have to take my airy kernel, and I have to just solve this integral equation where the limits are from xi to infinity. Okay, find out the eigenvalues and put it back here to evaluate this Fredholm determinant. Okay, so this was known before in the RMT literature. Okay, so what Tracy and Widom did is to actually evaluate this function. Okay, and they were able to calculate the the eigenvalues, if you like, and get the asymptotics, which is a very difficult mathematical problem. Okay, so I don't want to get into that details, but so this is the Tracy Widom. Okay, so it's not so easy computation, you can see, and to calculate the asymptotics in particular, and but at least I'll give you the asymptotic their results. Just get something here. And the proof that this is given by a Fredholm determinant, that the probability that the largest, because the probability that the largest eigenvalue is less than xi, means that there is no eigenvalue here. So this is what is called the whole probability. That means probability that there is no eigenvalue in an interval, and this you can always write in terms of this the kernel, and for determinantal process. And so the idea is just to put the scaling form of the kernel and compute this this object. Okay, so now, as I said, Tracy Widom original derivation is very hard to calculate this asymptotic properties of this. So this is Tracy and Widom, and but you can calculate the asymptotic properties. So this is this function here. You see, this is the PDF of the lambda max in the scaled variable. As I said, typical width fluctuation is n to the power minus 1/6, and it fluctuates from sample to sample, and you want to know what this PDF looks like, the scaled PDF. And it has two tails. So on the left side, it decreases very fast as exponential minus z mod xi cube. On the right side, it goes like xi to the power 3 over 2. Okay, so it's a highly non-Gaussian distribution. And okay, so this is okay. But if you want kind of simpler physicist derivation, if you like. So just give you a reference. Well, it's not that simple, but still, I mean, it's relatively simpler compared to the integrable system method that Tracy and Widom used. So this was, I'm not going to, give you the details, but this was like student of mine, Celine Nadal and myself. So if you are interested, you can just have a look at this. Because this has, this is more algebraic, sort of using orthogonal polynomial method, and so at least for me, it was easier to follow, to derive this Ponleve equation that Tracy and Widom did. So I'll not write down all these Ponleve equations and so on. But the main point is that the Tracy-Widom distribution is actually, after this derivation, as I said, it was staying dormant for a while, but then, so many different problems where this same distribution appeared, from directed polymer that Herbert already mentioned, Crepey's equation, random permutation problems, sequence alignment, large and gauge theory, liquid crystals, spin glasses, tiling problems that Filippo has worked on, and many other problems, okay? And in fact, now it has been measured in experiments. Herbert already mentioned the experiment of Takeuchi in liquid crystals, but it has also been measured in the coupled laser system, and also in disordered superconductors. And if you are interested, there are some popular magazine article. So there is one by Mark Buchanan in Nature Physics called The Equivalence Principle, and the other one by Natalie Olchover in Quantum Magazine, 2014. So at the far ends of any universal law. So you see the Tracy-Widom is at the central, and then it appears in so many different problems, and so on. So this is the sort of main thing about Tracy-Widom distribution. And yes. Right side, yes. Right side is actually very easy, because right side is related to the density. You see the probability, I mean, you can relate to the tail of the density, and then you can get it by WKB very easily, this 3/2. But the left side is much more harder, okay. So left side, okay, I don't have time to compute the, to talk about the large deviation functions, because you see the Tracy-Widom, if you look at this, so one important point I want to say here is that Tracy-Widom distribution is actually for typical fluctuations, okay. If you want to know the fluctuations here at the order square root of n, not of order n to the power minus 6, much larger fluctuations, they're actually, not given by Tracy-Widom distribution. So you have a large deviation tails, which are actually not given by Tracy-Widom, and this you can derive using the Coulomb gas method, okay. So this we had done with David Dean about 10 years back, and you can see a matching, and there, basically, so you see, to get this tail, you have to push this gas to the left, and whereas here, to get this tail, you just pull out one. So this is just an instanton method, basically. So it's actually very simple on the right-hand side, but left-hand side is, so in some other language, field theory language, or gauge theory language, this would mean the strong coupling phase, and this will be the weak coupling phase. But okay, let's not maybe divert too much. Yeah, sorry, yeah. Yeah. Yeah, no, think of this as a scaling function, okay? So, let me.
Previously, sort of near the edge, you indeed derive this scaling law for like the Ultracold.
Yes, that's the only scale that appears.
Sorry?
That's the only scale that appears.
That is sort of still covered in the hydrodynamic limits, say, of this distribution. But here, I mean, already just the variance of this distribution is not something hydrodynamic. I mean, you cannot derive.
No, you cannot derive by hydrodynamics. I never said you can derive it by hydrodynamics. This is, I mean, you do all this mathematics just to derive this limiting distribution. But if you are interested in, looking at fluctuations of order square root of n, okay, macroscopic scale, then you can use the Coulomb gas method, okay. But not finer scale. Again, I mean, I want to repeat again that Coulomb gas method is very good for when you are looking at fluctuations on a bigger scale, global scale. But if you're looking at a local scale, final, the fine tuning these things, then the Coulomb gas is not a very good method, okay, not appropriate, okay. So then you have to develop all these mathematical techniques, okay. Okay, so let me just see what more can I say, and then, okay. So one of the main conclusions from this part is that the free fermions in a harmonic trap at 0 temperature, it gives you a sort of physical realization of the Tracy-Widom distribution, okay. So this has not been, so we predicted that, the rightmost particle position at the 0 temperature will be Tracy-Widom distribution once you properly center and scale it. But, so this will be a sort of more direct measurement of Tracy-Widom distribution. You see, this Tracy-Widom distribution appeared in the, for example, the KPZ problem, okay. But the connection to KPZ is, to random matrix is rather, sort of convoluted, right? So, but here there is a direct sort of probing of RMT eigenvalues. And so this should give you sort of more physical relation of Tracy-Widom distribution. So we have been trying to convince the experimentalists to look into that. But, it's not so easy yet. But the cold atom experiments techniques are evolving very rapidly. So hopefully they should be able to measure within, few years' time. That this prediction, okay. So just to let me summarize, and then we'll finish. So, okay, so this is already said. So the positions of the fermions, so it forms a sort of, determinantal process. Again, process by process, I mean the joint distribution with kernel kn xx prime. And in the bulk, this kernel has this universal scaling form, sin z by z, whereas at the edge, it has this universal scaling form, which is the airy kernel. And also, the fact that, it's universal in the sense that you can take any potential of this confining potential of x to the power p, and, it really doesn't matter. Again, you can always linearize near the edge, and it will be always universal, and similarly in the bulk, it will be also universal, okay. So I think it's a good time to stop, and so what I'll do tomorrow is what happens at finite temperature. Okay.